Okay, well, today we have a real example from practice. Well, if you produce crude oil, generally many fields also produce a little bit of water and gas. Well, to separate the liquid phase from the gas phase is quite easy, but to separate the crude oil and the water is more complex. So on shore we sometimes use huge vessels in which we put the crude oil, but also in this crude oil a small amount of water is present as droplets. And what we do is we leave this crude oil for a certain time in this settling tank to separate the oil and the water from each other. But one of the questions you could pose is, how long does it take to separate these phases? Well, generally you take the smallest droplets in the top of the vessel and you calculate how long it takes before this droplet is at the bottom. So what you have to calculate is the settling time of the droplet in this vessel. Well, let's take out this water droplet, which is falling down. Well, it's falling down by gravity and is counteracting by a buoyancy force and by a drag force. And so in a steady state situation, you have to set up the balance, and you could see that in this case the gravity force is equal to the buoyancy force plus the drag force. Well, you can solve this problem by substituting all these values. Well, the gravity force is of course the mass multiplied by the gravity constant, and similar is the buoyancy force. However, if you combine these two, you get a balance which is Fg minus Fb is equal to the drag force. Combining these, we substitute the mass and the gravity, then we get the difference in density multiplied by the volume multiplied by the gravity constant is equal to the drag force. Well, we assume that we may apply Stokes Law here. And Stokes Law says that 3 pi multiplied by the diameter of the water droplet multiplied by the viscosity multiplied by the settling velocity. This is Stokes Law. And if you apply this, you can calculate the velocity. Of course, if you substitute it, you get that the settling velocity equals, well, let's write it out, divide by 3 pi d mu is equal to, and I put it here, is delta rho multiplied by d squared multiplied by the gravity constant divided by 18 times the viscosity. This is the settling velocity, but we are interested in the settling time. Well, the settling time, then we have to know what the height is of this vessel, because otherwise we can't calculate this. So in this case, we could say that the time needed is the height divided by the settling velocity. And if you would calculate this, you come to 20.4 hours. What you have to check, because we have assumed here that we use Stokes Law, but is this allowed in this case? Are we allowed to use Stokes Law? To do this, we have to check the Reynolds number. So the Reynolds number, which is the density multiplied by the settling velocity and the diameter divided, should be much smaller than 1. Well, if you substitute these values, you get a Reynolds number which is far lower. So in this case, it is allowed to apply Stokes Law. Well, this is an example how you can calculate how long it takes for the settling. On the other way around, you could also use it for design purposes. What is the height of the tank? So the other way around. Okay, thank you.